Hello and welcome to Chapter 12. In Chapter 12, we're going to look at applications of the derivative. And unfortunately for you, we have a new rule. If you need to use it, you have to simplify it. So start simplifying your derivatives. You're not just finding a derivative just for kicks. Now you're going to use it. So we're going to make the algebra easier. Here we go. Here's this random graph I drew, all right, with various values marked on it. Section 12.1, we're going to talk about maxima and minima. So let's start with a relative extrema. F has a relative maximum at a x value of c if there is some interval from r to s, even a very small one, that contains c for which f of c is greater than or equal to f of x for all x between r and s for which f of x is defined. And that's totally a math definition. What that says is, in this case, our function f has a maximum at x equals a because for this small neighborhood around it, f of a is the highest point. Let's pretend I could draw it right there at the highest point. All right, so that's a maximum. But on the same scale, let's go with green, I guess. F has a relative minimum at c, just a general x value of c, if there is some interval from r to s, of even a very small one, that contains c, for which f of c is less than or equal to f of x for all x between r and s, for which f of x is defined. Again, a very mathy definition. But what that means is here, at an x value of e, we have a minimum. Because in this small area, this f of e is the lowest point on the graph. Yes, over here, there's a lower point. But in this area, it's the lowest. So it's a relative minimum. All right, this is also a minimum. F of b is a minimum. How do we compare the minimums? We don't care. We know in this little area, this is the lowest the graph gets. In this little area, this is the lowest the graph gets. That's all we care about with minimums. Similarly with maximums, in this little area, right, that's the highest our point's going to get. In fact, in this little area, right, we also have a maximum. But notice the graph goes up forever, and it goes up forever. There's going to be a higher point. But in this little area, that's as high as it gets. And that's all that relative extrema, whether it's a maximum or a minimum, that's all that means. Now, absolute extrema. F has an absolute maximum, or if f at c, if f of c is greater than or equal to f of x for every value in the domain. So this graph will not have a maximum because it goes forever up. This graph will not have a minimum for the same reason. It goes forever down. There's no low value. But we might look at something like a parabola that opens downward. This is an absolute maximum. It absolutely never gets higher than that value, ever. Maybe we have an absolute minimum. Maybe we have this weird graph, one of our little W-shaped graphs. Straight lines are overrated. I apologize for what that looks like, especially after I add a dot to it, but we can see that the graph never gets lower than this value. This is the absolute minimum. Absolute minimum of the graph. It never gets lower, ever, ever. This relative, sometimes it gets higher, sometimes it's lower, but in this little neighborhood, think of this as your little neighborhood, whereas this is the whole city or state or country, whatever you want to. Locally, I've got the best house. But on a global scale, absolutely, I don't have the best house in the city, even in the, I don't know, on the block if I really think about it. Okay, so the extreme value theorem is going to take these types of extrema into account. If f is continuous on a closed interval from a to b, then it will have an absolute maximum and an absolute minimum value on that interval. So all we have to check is f continuous on a closed interval, then this is guaranteed. Absolute maximum, absolute minimum guaranteed. Each absolute extrema must occur either at the end point or a critical point. Therefore, the absolute max is the largest value in the table of values of f at the endpoints and critical points, and the absolute minimum is the smallest value, right? Maximum big, minimum small. So endpoints, we know what the endpoints are. That's when x equals a and x equals b, but what is a critical point? We need to know what a critical point is. Let's go with how to find critical points, even though I didn't really give you a definition here. If f is a real valued function, then its relative extrema occur among the following types of points, collectively called critical points. Okay, so these are our critical points. We have stationary points. F has a stationary point at x if x is in the domain and the derivative is 0. To find stationary points, we find the derivative, set it equal to 0, and solve. Okay. Also a critical point is what's called a singular point. F has a singular point at x if x is in the domain and the derivative is not defined. So it exists for the function, right? We could use x in the function, but we cannot use x in the derivative. To locate singular points, find values of x where f prime of x is not defined, but the original function is defined. Okay, so stationary, singular, and then the endpoints. The x-coordinates of endpoints are the endpoints of the domain, if any. Recall that closed intervals contain endpoints, but open intervals do not. All right, find the exact location of all relative and absolute extrema of each function. Also determine the intervals on which the function is increasing and decreasing. What? We haven't even talked about that yet. Let's take a look at number 1. Our function is 2x squared minus 2x plus 3 with a domain from 0 to 3. Now, we already know, right, because this is a 2x squared, it's a parabola, it opens upward because the 2 is positive, so we know it's going to have we know it's a parabola, right? It's going to look something like this. So it's going to have a decreasing part, it's going to have an increasing part, and it's going to have a minimum. I can't get all the letters there. Let's suppose that's called a minimum. How do we find that? If to find the exact location of all extrema, critical points, first we find where the derivative is 0, and then we find where the derivative is not defined. So stationary points, find the derivative. Derivative of 2x squared minus 2x plus 3 is 4x minus 2 plus 0, so 4x minus 2. Stationary points occur where the derivative is equal to 0. I'll keep those in blue on this page, this video. 0 equals 4x minus 2, add 2 to both sides, divide by 4, and I find x equals 1/2. So x equals 1/2 is a point that I need to take a look at. It's critical for some reason. Stationary. Singular point. Is there any place where the derivative is not defined? And really, to find where the derivative is not defined, we're looking for domains, right? This linear function is defined everywhere, so there are no singular points. And I find my endpoints, x equals 0 and x equals 3 from the given interval. All right. Always, I can't stress this enough, always use the original function to find y values. For any y values you want to know, always use the original function. Okay, so I use an endpoint, x equals 0. F of 0 is 3. I use my 1/2, right? F of 1/2, I put 1/2 in everywhere I see an x. I'll have 1/2 squared is 1/4. 2 times a quarter is 1/2. Here I have 2 times a half, which is 1. So I have 1/2 minus 1 plus 3. So that's a 2.5. And I also have my other endpoint, x equals 3. And I put these in order. That way when I'm looking at them, I can kind of see how the function goes along as if we were looking at it from left to right. When I evaluate f of 3, I get 15. Now, continuous function on a closed interval, it has an absolute maximum, output of 3, output of 2.5, output of 15. 15 is the biggest number. That's our absolute maximum. Now I'm looking at 3 and 2.5. 2.5 is smallest. It's smaller than 15 also. So that's my absolute minimum. But what's going on with this relative maximum? Remember, my graph is coming down. So here at 0, it's a relative maximum, but it's not the absolute maximum. What it seems is that f is decreasing. for x values between 0 and 1/2, right? It goes down. And then once the x values hit 1/2, the y values start increasing again. And so the function is increasing for the x values between 1/2 and 3. We know what the general graph looks like. We see what the number values tell us. We describe the pattern based on that. All right, number 2. F of x equals 2x cubed minus 6x plus 3 with the domain from -2 to 2. My first step, always when I'm looking for critical points, I find the derivative first. My derivative will be 6x squared minus 6 plus 0. So 6x squared minus 6 is my derivative. Set it equal to 0 to find stationary points. If 0 equals 6x squared minus 6, I can factor out a 6, and then I divide both sides by 6. Right here, I divide both by 6. 0 divided by 6 is still 0. Awesome. 6 divided by 6, I just have that x squared minus 1 left. And we know that if 0 is equal to x squared minus 1, we could add 1 to both sides, take the square root. Remember, when you take the square root, you have to include the plus or minus, because it could be either one. We don't know. So we get x equals plus or minus 1. Endpoints. The derivative is a polynomial, so the derivative is always defined, so there are no singular points. All right, no singular values, no singular points. So I look. Okay, I have -2, -1, 1, and 2. I'm going to evaluate f of -2, f of -1, f of 1, and f of 2, always in the original. Always in the original function to find my y values. When I put -2 in for x, I'll get -1 out. If I put -1 in for x in the original, I'll get 7. And I keep evaluating. F of 1 equals -1, f of 2 equals 7. So I know the only places where maximums and minimums can occur are these 4 x values. These are the corresponding y values that go with them. And I notice that 7 is the biggest number and it happens twice. Those are both maximums. Closed interval. So we have 2 absolute maximums because they're the same height. The only numbers remaining are both -1, which means they're both the same lowest number. So these are minimums. So think about this. If a graph is at a low point and then it goes to a high point and then it comes to a low point and then goes back to a high point, it's increasing, right, between -2 and -1. And then it decreases from -1 to 1. All right, it has to come down to this dot. Think about connecting the dots. And from 1 to 2, it has to go back up. So we could get the increasing and decreasing simply from the y values and looking at how can I get there with a smooth curve. I must increase, I must decrease, I must increase, and keep rolling from there. All right. Cool. Well, let's add to this. Suppose that c is a critical point of the continuous function f, and that its derivative is defined for x values that are close to and on both sides of x equals c. All right, and on both sides. Then determine the sign of the derivative to the left and to the right of x equals c. Okay. At x equals c, we have something going on, right? Either the derivative does not exist or the derivative is equal to 0. If f prime, the derivative, is positive to the left and negative to the right, it's because, make sure I do this correctly. I drew my line wrong. Positive is increasing, negative is decreasing. Oh, look at that. We have a maximum. So if the derivative changes from positive to negative, we know we'll have a high point on our graph. Number 2. If f of x is negative to the left and positive to the right, what's happening? Well, negative means the slopes are negative. Slope is going down. The graph must be decreasing there. Derivative, slope, positive means we're increasing there. What do we have? We have a minimum. So if the derivative changes from negative to positive at c, we have a minimum. Now, if it's the same sign, we got nothing. It has to be a change. We call this the first derivative test. If the value of the derivative changes from positive to negative or negative to positive, if it changes at C, then we know we have either a maximum or a minimum, depending on which one it is, at C. If it doesn't change, we don't know. Actually, it's not a minimum or a maximum. So check out this sign chart we're going to use to test for sure where a function is increasing and decreasing instead of just using the rationalization we used in the previous examples. All right, so still finding all that stuff. F of t is t cubed minus 3t squared with a domain from -1 to infinity. Notice we include -1. First thing we do to find increasing and decreasing or find extrema, minimums, maximums, first thing we always do is find the derivative. Derivative of t cubed is 3t squared. The derivative of minus 3t squared is minus 6t. To find stationary points, we set the derivative equal to 0. If 0 equals 3t squared minus 6t, I could factor out a 3t. What remains when I take 3t squared and I divide by 3t is a single t. Still have the minus sign. 6t divided by 3t is 2. Now, if two things multiply together to give me 0, either one is 0 or the other one is 0. It's the cool thing about 0. No other number, it works like that. So if 3t equals 0, then t equals 0. Or if t minus 2 equals 0, then t equals 2. I have two values to consider as stationary points. The derivative is a polynomial, so there are no singular points. And the only endpoint I have is on the left at an x value of -1. So I have -1, 0, and 2. These are my critical numbers. These are where things might happen. So I always want to go back to the original, always the original, in black, the original function, to find the y values. Okay, so f of -1, I put -1, -1 cubed is -1, -1 squared is 1, so I'll have -1 minus 3, so it's -4. I'll try t value of 0. If I put 0 in for t, I get 0 out. If I put 2 in for t, 2 cubed is 8. 2 squared is 4, so 8 minus 3 times 4, that's 8 minus 12, which is a -4. I can look at these and see that -4 is the smallest number that appears from my critical values. -4 tells me that's where my minimum is. 0 is the highest number in my table. That tells me where my maximum is. But check this out. That's what we knew before, right? Here's what a sign chart can tell us. So for our sign chart, what I'm really doing is I am cutting this off at -1. Using a test value of -1 is a little cheap, but I'm going to fix that. I don't have the rest of this. This whole thing starts out at -1. So if I really wanted to be good about this, I really should check the -1/2. F of -1 is on an endpoint. It is a critical number. I really shouldn't have checked that. I should have checked at a -1/2. So I'm going to do it as a fraction here because that decimal's not working out very well for me. The derivative, I'm using the factored version here. So I had 3 times a -1/2. That's the value, right? I want to see what the sign of the... Let me set this up. I didn't even set this up. So I put in 0 and 2 because those are my stationary points. I have no singular points to include. I have an endpoint, so I really should have capped this at -1. This, I shouldn't use it. That's not fair to use. What I should have used instead was a value between -1 and 0, between my critical values. And the easiest one is a -1/2, or a -0.5. So what I'm going to do is I'm going to choose -1/2, and then I'm going to use 1, and I'm going to use 3. So I need to use a value between -1 and 0, a value between 0 and 2, any value will do, and a value larger than 2. All of my test points are going to go up here. And the value of the derivative, not value, the sign of the derivative is all I'm looking at. I'm looking at whether it's changing positive to negative or not. Okay. Here we go. So if we evaluate f at negative 0.5, we can evaluate f prime. I could evaluate here, but I'm going to evaluate the factored form, and I'm going to tell you why. Don't worry. Negative 1/2, I'm going to write it correctly. Negative 1/2 minus 2. So I have my 3. I have my t value. I have chosen to be a negative 1/2. And I put in my t value again, a negative 1/2. Here's what I know. I know that I'm going to have 3, which is positive. I don't even care that that's 3. I care that that's positive. That negative 1/2 is going to be a negative. Negative 1/2 minus 2, that's another negative. If I multiply a positive times a negative, my result is positive, right? And I multiply 2 negatives, it makes a positive. So all I really care about is that my graph is increasing in between a negative 1 and 0. And it makes sense, right? So it's increasing in there. And so I draw an arrow, I put a plus sign, I draw an arrow indicating it's increasing, and then I check my next value. In between my stationary points of 0, 2, I use a test value of 1. I put it in. 3 times 1 is 3. 1 minus 2 is negative 1. I don't care that that's negative 3. I just care that it's negative. The number couldn't care less. How often do you say that in a math class? But we really don't care. We only care that it's negative. It's negative. The slope is, the derivative is negative in between 0 and 2. So we're decreasing. And f of 3, we find our derivative is positive, so it's increasing. We have a maximum at x equals 0. We have a minimum at x equals 2, as we assumed, as we saw here. But also, we know the graph is increasing between negative 1 and 0. Notice I did not include negative 1. That is an open bracket because you cannot increase at negative 1. At negative 1, you're hanging out. You cannot include it. So from negative 1 to 0, our graph is increasing, has a positive derivative. Between 0 and 2, our graph is decreasing. We have a negative slope or a negative derivative. And from 2 to infinity, the rest of the graph, we will be increasing. All right. So we can break it down using these test values. I promise this next one will be quicker because this video is getting too long for me already. Here we go. F of x is x plus 1 to the 2/5 with a domain of negative 2 to 0. To find the derivative, we bring that 2/5 down in front. Leave the inside alone. Subtract 1. 2/5 minus 1 is 2/5 minus 5/5, which is negative 3/5. Don't forget to multiply by the derivative of the inside. I put the 1 just as a reminder. 2's in the numerator, 5's in the denominator. The 5th root of x plus 1 cubed ends up in the denominator. I don't use rational exponents. I try to put it in terms of roots and radicals, and I don't know why. Now, to find critical points, right? We set the derivative equal to 0. Well, think about when you're solving a fraction equal to 0. The first thing you're going to do is multiply both sides by b. And so you end up with 0 equals a. If you want to know when a fraction or a rational expression is equal to 0, it turns out you really only have to find when the the numerator is 0. 2 is never 0. So there are no stationary points with this. That means the derivative is never equal to 0. But notice we finally have a singular point. The original function is defined everywhere. I could put any value of x in, it's all good. But in the derivative, negative 1 will cause a 0 in my denominator, and we don't do 0 denominators. So negative 1 is a singular point. It causes an issue with this particular graph. Our endpoints, negative 2 and 0. Always blue, green, gray. Okay, so knowing my values, negative 2, negative 1, 0, I put them in the original function. I evaluate, I can find my maximums, the highest one, my minimum, the lowest, Notice I didn't have absolute maximums or minimums on this particular function because of because of the interval. My goodness, I couldn't think of that word. This is a closed interval. This was not a closed interval. I was not guaranteed absolute max and mins here. I do have mins and maxes there, but I'm not guaranteed absolutes. Here I'm actually guaranteed absolutes. Absolute max and absolute mins. Now, I want to know about increasing and decreasing. So I put a very limited number line. This is my test line. I start at -2 and it ends at 0. -1 is my only singular point. So in between -2 and -1, I choose a test point. I chose -3/2, -1.5. In between -1 and 0, I choose a test point. I used -1/2. These test points go into the derivative. I want to know what the slopes are. I want to know if the function is increasing, slope's positive. If the function is decreasing, slope's negative. So when I substitute a -3/2, I have a -3/2 plus 1, which is a -1/2. -1/2 cubed, still negative. The fifth root of a negative, still negative. I'll have 2, which is always positive, over 5 times a negative number, which is negative. Do I know what that number is? No. Do I care? Also no. Isn't that awesome? I only care if it's positive or negative. And a positive divided by a negative is always negative, so I know my slopes are negative there, even if I don't know what the number value is. When I choose a -1/2 and I put it in, -1/2 plus 1, that's positive. A positive value cubed is positive. The fifth root of a positive value is positive, and 5 times a positive number is positive. 2 is always positive, and a positive divided by a positive is positive. So I know my derivative is positive between -1 and 0, because nothing happens until I get at -2 or at -1 or 0. The rest of the time, it's just being constantly whatever it is. So if my slopes are negative, my graph is decreasing. If the slopes are positive, my graph is increasing. And I can see I had the max, min, max correctly identified. I can see that my graph increases between -1 and 0. My graph decreases from -2 to -1. And I try to always write my intervals so I can see the whole thing, right? From -1 to infinity. -1 to 0, then 0 to 2, and then 2 to infinity. My whole interval from -2 to 0, -2 to -1, and then -1 to 0, I can see the entire combination of it there. All right, last one. And of course, it's a big one. If you want examples, it gets long, but all the lesson was earlier. So if you're bored, if you get it, move on. You don't have to watch the whole thing. Thanks for hanging around. But here's the last example if you want a really detailed, good one that has everything going on. F of t is t squared plus 1 over t squared minus 1 with the domain of -2 to 2. Notice the original function is not defined at t equals plus or minus 1. Original function, keep in mind what its domain. So it's actually from -2 to -1, and then to +1, and then to 2. -2 to -1. Oh, we can't use that point. But from -1 to 0, or excuse me, to 1, we're good. But can't use that point. And then from 1 to 2, we're good. We take the derivative. Super excited to use the quotient rule. That's low t squared minus 1. D high derivative of t squared plus 1 is 2t. Minus high t squared plus 1 times the derivative of low, which is 2t. All over t squared minus 1 squared. Distribute. You're going to use this. You have to simplify this. 2t times t squared is 2t cubed. 2t times a minus 1 is minus 2t. 2t times t squared is 2t cubed, but remember that minus sign. And again, I'll have a minus 2t. 2t cubes cancel out. I have negative 4t in the numerator and a t squared minus 1 in my denominator. Again, if I want to set a rational expression equal to 0, that's when the numerator is 0. So 0 equals negative 4t, so t must be 0. When is a rational function undefined? It's undefined where the denominator is 0. So rational function equal to 0 Numerator, rational function undefined, denominator 0. But notice the original function's not defined at plus or minus 1, and the derivative's undefined at plus or minus 1, so they're not singular points. If the function was defined there and the derivative not, that's when they're singular. They're not singular points. It turns out these are asymptotes. Asymptotes when they are asymptotes when it's not defined in the original and the derivative. Sorry, I lost track of what I was thinking there. It happens when I've been talking for 30 minutes in a row. When we look at these values, if I substitute my endpoints and my stationary points, f of negative 2 is 5/3, f of 0 is negative 1, and f of 2 is 5/3. It's weird, but because this is not a continuous function on a closed interval, right? It's not continuous. It turns out that 5/3 is a minimum, negative 1 is a maximum. That doesn't seem reasonable, but it doesn't fit that closed interval continuity thing. So let's see what's really going on. Well, we have negative 2. We have negative 1. That's an issue just in general. We can't use that at all. 0 is a stationary point. So we have an endpoint, a domain issue, a stationary point, a domain issue, and an endpoint. So I'm going to use test values in between negative 2 and negative 1, negative 1, 0, 0, 1, and 1, 2. And I just chose all the halves, and instead of calling it 1.5, I called it 3 halves because I'm a mathematician, not a baker or a carpenter. In general, notice that this denominator of our derivative is always positive. What's a negative times a negative? Positive. What's a positive times a positive? Positive. What's something squared? It's always positive, as long as it's not 0. Right? So denominator is always positive. As I use my test values, I'm looking at negative 4 times a negative 3 halves. That's positive over a positive. But negative 1 half, same thing. That's negative 4 times a negative 1 half. Oop, there we are. Negative 4 times a negative 1 half. That's 2 negatives make a positive. Always over a positive. When my t value is positive and I multiply it by negative 4, my numerator is now negative. So thinking about this, at negative 3 halves, I have a positive derivative. Negative 1 half, I have a positive derivative. Positive 1 half is a negative derivative. Positive 3 halves is the negative derivative. Here's what's going on. From negative 2 to negative 1, I'm increasing. But there's no maximum there, because on the other side of negative 1, I'm also increasing. Weird, right? So increasing is from negative 2 to negative 1, and again from negative 1 to 0. I can't go from negative 2 to 0 because there's an interruption in the function. I can't use that value, so I have to designate that it splits and starts again. Notice on the left of x equals 0, actually t equals 0, on the left of 0, my derivative is positive. On the right, it's negative. So I've found a maximum. Cool, right? A maximum. Notice at negative 2, I'm leaving it. The derivative's increasing, so that's why this is a minimum. I have negative, negative, so it's going down. So I have no relative, I have no maximum or minimum. It doesn't change signs. And then at 2, that's where our interval ends, and so that's going to be a low point because it was going down into there. And I have my decreasing set here as well. Oh, so dry, 30 minutes without a drink. But I thought to myself, if you're in it this far already, let's take a look at this, right? Let's take a weird at this weird but true part. I'm going to use my calculator. I'm going to see if I can put it, I'll put it over here, I guess. Other things I was working on. X squared. When I'm using my calculator, I use x squared instead of t squared. Notice I am entering the problem wrong. I'm also using parentheses around the entire numerator, parentheses around the entire denominator. Just because my calculator is not as smart as I am, and your calculator is not as smart as you are either. It's just faster, a lot faster. So what's going on with this graph? We said f of 2 is 5/3, which is a minimum. F of negative 2 right here is negative 2. And it does happen to, it's because the graph ends at negative 2, that's going to be a minimum just because this part of our graph doesn't exist. Right? If our graph stops, I can make that stop at negative 2, but it would take way too much of our time, and we don't want to deal with that. A value of negative 1 here is a maximum in this little location near it, right? That's the highest value. And if our graph stops here at x equals 2, that will be the lowest part on that right-hand branch. Crazy but true. Sometimes you could see it with just calculus, right? What is it doing? It's increasing, and then it's increasing, and then it's decreasing, and then it's decreasing. And our calculus told us all that. Calculus is way better than algebra. Algebra is the hard part. Thanks for listening.